Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Zurich. Quick thanks to our sponsors, the National Centre of Competence in Research on Dependable Ubiquitous Automation, the International Federation of Automatic Control, and the IEEE Control Systems Society. Our guest today is Munther Dahleh, William Coolidge Professor of Electrical Engineering and Computer Science at MIT. Welcome to the show, Munther.
Thank you, Alberto. It's a pleasure to be here.
So today I'm proud to say that it's the first time that we have a podcaster also on the other end.
Yes.
We're going to touch on Data Nation, I guess at some point, your podcast. But I should start this episode by saying that it was very difficult for me to put you into a box as I was preparing this episode. Your research spanned several different fields. Of course, you started in control theory, but then you ventured in many other fields like statistics, economics, energy, transportation, and whatnot. So it was quite difficult on my end to frame you.
I can make a comment about that. Even though a lot of the stuff looks very different, I mean, at the end of the day, I am a control and a decision theorist. And within all of these problems, decisions are the most important thing. And so somehow, control theory and decision theory sort of training got me into these different types of fields. I probably do the same thing anyway in all of them.
In fact, I mean, as we were speaking also prior to the podcast, this came up when we were discussing about the creation of the Institute for Data Systems and Society, that your thinking is still very much grounded in decision and control thinking. So perhaps I tend to always go chronologically in this podcast. I was wondering, how did you happen to work in the area of controls? And basically, how did your journey start in this field?
It's quite interesting. A lot of times people ask, how much planning have you done in your career and how did you pick something? And my observations about my own trajectory is a lot of stuff happens. Either the opportunity presented itself or there was a chance that you landed there and you found yourself doing it. It started for me in college when I took linear algebra, to be honest with you. And I thought linear algebra was amazing. Such a beautiful field, it's so complete and elegant and so forth. And I was talking to people about linear algebra, and my undergraduate was in electrical engineering. And somebody mentioned you should take control theory classes because they use linear algebra. I didn't even know. And so I started taking controls and using linear algebra, and that's where it started. Honestly, it wasn't a sort of an intrinsic interest in control that got me there. What got me there was actually my love for mathematics and linear algebra.
Nice. I remember joking at college myself with other people that they were referring to control engineering as matrix engineering.
Yeah, it's true. It's true. You discover that it's a lot more than that, but that was kind of the beginning of it, right? And what kept me tied to control theory was the elegance of the field, the beauty of a lot of the structures and the solutions that we had. And initially I was not interested in applications. Over my journey, as you described it, I've changed a lot and I got interested in more applications. But to be honest, at the beginning, it was just, this is a beautiful field and let me study it.
So talking about college, actually, you started at Rice University in Houston, right?
I started at Texas A&M for my undergraduate.
Okay.
And then I went to Rice for my PhD. And so it's at Texas A&M that I actually began this journey as an undergrad. I studied under Shankar Bhattacharya, who just passed away. And he was the one who was telling me, you should take these advanced courses in control. And so I took a graduate level course that he was teaching from Mary Woonham's book on geometric control theory. And that was kind of like linear algebra on steroids.
Yes. Delightful book, by the way. It's an amazing book.
Yeah. And then because of that, I decided to apply to work with Boyd Pearson at Rice because he was the advisor of Shankar Bhattacharya. And because of that link, I started looking at the papers and the work that he was doing, and I got excited about his research, and I applied to go and work with him. So there was a little bit of a chain reaction there that got me to Rice. It wasn't random that I went to do my PhD over there.
And as we discussed also in some previous episodes, at this point, also Mustafa Hamash and Bassam Bamie have already been in the podcast. We've already come across the fact that you guys were all at the same time in the same place, at least for some portion of your graduate studies.
That's correct. And we were also roommates.
I don't know, that I didn't know. And so the topic of your PhD was L1 control, right?
Correct.
So L1 control, I guess it would be nice to give to the audience maybe a brief overview of what that was and why it was an open problem at the time.
Sure. So first of all, I think I joined the control theory at the peak of robust control and H-infinity optimal control. And I started in 1983, and in 1983 was just about the time when the major papers that came by Chan and Pearson, and then Francis, Hilton, and James, I don't remember the exact sequence of papers, have just come out on the solution of on the one block H-infinity problem. And so I was really excited about that field and looking into it. Robust control is a very powerful paradigm. And even though actually it was developed primarily at the beginning for linear time invariant systems, it really has nothing to do with linearity. It's a way of thinking about how to design systems and how to represent uncertainty as part of the problem formulation, as opposed to a posterior thing that results, I've got a controller and it has some robustness or stability margins. It's really putting the robustness up front and designing the controller to accommodate for the uncertainty that you have. So it was a beautiful paradigm. H-infinity was also a very elegant theory. And then there were a lot of conversations about what happens if the class of disturbances that you wanted to reject didn't have the nice structure of a finite energy or a bounded L2, what we call bounded L2 disturbances. There was a story behind this, and I'm happy to tell you how this whole thing happened.
Oh, yeah, sure.
Yeah, so my advisor gave me a paper to review, and the paper was written by Vidyasagar. And the paper described the importance of the L-infinity disturbance rejection problem. And I think at that time he has started working in robotics, and he has recognized that many of the disturbances that you want to remove from the system are not finite in energy. And the finite energy assumption sort of makes the theory somewhat awkward, the H-infinity theory awkward. And so he talked about the L1 optimization problem and talked about why that problem was a little challenging because it didn't follow the Hilbert space and the beautiful L2 sort of structures. And my advisor gave me the paper to review, and my advisor is a little bit detailed oriented, and he was saying, well, but this is a paper that formulates and talks about a problem but doesn't solve it. There were solutions in some special cases. And I read the paper and I was very excited about it. And I said, I think it should be published because how else people would know that this is an important problem, Yeah. I mean, it cannot be kept as a secret. So we have to kind of tell people that it's an important problem. But I didn't start working on it. I looked at the paper and I recommended to my advisor that it should be published, and the paper was published. And it was in the meanwhile that I was actually studying something else that it dawned on me to go back to that problem and say, oh, wait a minute, what was going on there? Why was that problem really hard? And I was actually sort of looking at some duality architecture structures for certain optimization problems. And I said, why wouldn't I be able to apply this for that problem? And that what got me back to the problem. But the exposure really came from Vidyasagar's initial paper.
Nice. I obviously didn't know this. Very interesting. I guess maybe just to clarify for the audience, when you say L-infinity signals to reject in robotic applications, I imagine that you're thinking about vibrations, because probably those are signals like sinusoids that have a finite L-infinity norm, as we say in controls, but not a bounded energy or finite L2 norm.
That's correct. So you have these types of persistent disturbances that also are not periodic in nature. So vibrations, but sort of have nonlinearities and high harmonics and things that are persistent in nature, where the energy is accumulating over time, but it doesn't have periodicity where then you can sort of think of them as sort of finite energy signals. So that's kind of the class of disturbances. And from a practical perspective, really, almost all disturbances are persistent. And you can argue in some ways that the finite energy or the finite power type signals are an idealized assumption, right? It's a nice assumption, but it's an idealized assumption. In the sense of approximation, it does make sense to focus on a particular frequency range and so forth. But the L1 theory came as a way to think about time domain entirely and to think about the fact that these things are, the characterization of frequency isn't relevant in this context. Of course, it's relevant in design, but in this context it's not. And it yielded design methods that are linear programming algorithms, which in some ways brought us to computational approaches for designing controllers. So now that I'm in the realm of solving linear programming problems, I don't have to worry too much about the structure of the solution and how analytical the Riccati equation and so forth. It's all another linear program. And the techniques using duality theory that were developed for the L1 problem extended to solve problems with multiple objectives. So now you could have disturbance rejection, but you also have some robustness, and maybe you're tracking specific signals. All of these translated into multiple objectives in terms of linear constraints, and the technology developed for L1 applied for these types of problems, which was really nice to kind of allow us to begin to have a computational environment for providing solutions. And having computational environment is good because it's not always that you're going to take the controller that you designed from this and plug it in. That's not really how design works. But what you get is the limits of performance. And you recognize from these particular techniques what can be achieved and what cannot be achieved. And then you may come up with a much simpler controller that will get you in a good trade-off of where you want to be. So a lot of these solutions really were about fundamental limits and not necessarily about just the design that comes out of the controller.
This is very much in the spirit of the philosophy of robust control. We've talked about it also previously in the podcast with other guests. I should say also, we haven't mentioned it yet, but this stream of research results in a paper called L1 Optimal Feedback Controllers for MIMO Discrete Time Systems that gets the Axel V Award prize. I wonder whether that was your first paper?
That was my first paper.
It's quite a funny story.
Yeah.
And one more thing that I wanted to add is that we keep on speaking about L1, but I don't think we actually mentioned why we talk about L1. L1 is the norm that is induced by considering L infinity signals on a particular operator. And that's why we talk about L1 optimal controllers.
That's correct. I have a little story about the paper.
Yeah, sure. Please.
Actually, two stories embedded in one story. So the first thing is that I showed the solution to Boyd Pearson, and the solution was really simple. It was not actually, the problem has a very nice and simple solution, particularly in the single input, single output case. And he wasn't familiar with the techniques, the mathematical techniques that I was using for this problem. So he was a little skeptical whether this is too simple to be true, and he took it upon himself to review a lot of the methods and so forth. It took some time, came back, and then he said we should submit this. But before we submitted, he wanted to show it to Vidyasagar.
Oh, wow.
Yeah. And I believe that he was actually invited at that time. Vidyasagar was in Waterloo, and they were good friends. And so, but also, I think the situation, maybe Vidyasagar, if he hears this, would correct me. Boyd was going to be an outside examiner for one of Vidyasagar's students. So he was there and he shows him the report. And I think Vidyasagar looked at it for 15 seconds. I think that, he's a brilliant guy, right? He looked at it for 15 seconds and said, oh yes, that is a correct solution, something like
Wow.
that. And, So it's a very funny story about this. So then when my advisor came back, he was very excited and he said, okay, let's submit this for publication. So I kind of added a few sentences here and there, and I submitted the paper. This is the multi-input, multi-output case. It was 8 pages. 8 pages, right? And because you said, is this your first paper? That was my first paper. It was 8 pages. I mean, literally, I think there were no English in between the math. It was just equations, right? And a lot of it was, it's easy to show, it's obvious to do, blah, blah, it's like, so we sent it for publication and got rejected. And it got rejected. It's like, this is not how you write a paper. Yeah, there has to be some English in between the math, which is interesting, right? So then I had to rewrite the paper and explain a lot of the steps and motivate the steps and so forth. So it became a 45-page paper. So there was a bit of a learning experience for me in this first paper, got them to actually go from rejected to getting an award. But it was literally, I mean, I laugh at the story and I tell my students the same thing, is that it's often the case when you write your first paper. I mean, you write something that first you think is obvious to you, but it's not obvious to everybody else. I mean, they haven't been thinking about this, so why would it be obvious? And the second thing is actually you still don't know how to write really to motivate a problem. And so it was a learning curve for me, a very steep learning curve, particularly when the paper was rejected. It was like a shock, Anyway, that's my story.
Amazing. I guess what we can add to this is that this line of thinking also resulted in, at least to the best of my knowledge, 2 books at least. One called Control of Uncertain Systems, a linear programming approach, and then a second one called Computational Methods for Controller Design with Ignacio Diaz-Bobillo and Nicola Elia.
Correct.
Together with several other publications. Obviously, due to restriction of our time together, I will probably skip several publications that we will not be able to mention. But what I would like to mention is that after your PhD, then you transition and you move to MIT directly. Is that correct?
That's correct.
And so there you start interacting, obviously, with local faculty. Something that piqued my interest a lot was a paper that I've seen that you wrote with Sasha Megretsky and Jorge Gonzalez.
Yeah.
On relay feedback systems, just because I thought that you seem to have a taste for open problems, or at least, to the best of my knowledge, proving global stability of relay feedback systems at the time was open, if not...
Yes. It was a really interesting problem. And I think that, not to get into the details and so forth, but part of it is also, Poincaré maps and the ability to sort of construct a Poincaré map was well known, but with these types of problems, these maps were discontinuous and were very difficult to analyze. And so we used these kind of LMI relaxations as a way to prove these types of results. It was an interesting body of work that I did with Sasha. And just to say also, when I got to MIT, I also started interacting with John Tsiklis, and I credit some of my kind of breadth in the research to some of these collaborations with people that were doing things different than what the core control community was doing. I mean, John is a control person, but also did a lot of different work. And so we started thinking about the problem of statistical learning theory from a foundational point of view, which I have come a full circle to work on that problem in the last few years. But so that was interesting that in the early 90s, we were working with one of our students, David Say, who's now at Stanford, on the question of what is learnable. And so much about the limits rather than the algorithms for learning. What are the sort of model structures that can be learned from finite data? So these collaborations that started at MIT actually were also influential into my trajectory.
In shaping the way you think. In fact, actually, I was curious about when did you start thinking about data? Because then it starts to become, data and algorithms, as you say, to learn. It starts to become more and more prevalent in your research, and also how to apply these concepts to societal problems. So things that affect us in the everyday.
Yeah, I think that in the early 90s, there was a large effort among the controls community to connect learning to controls. And so what we refer to as the L4CD right now, which is sort of, I think that has started a few years ago, actually was also there in the early 1990s. And there was a large number of people from Europe and the United States who was interested in doing very interesting work on those types of problems. I think the difference for us in the 90s is that there just wasn't enough data to make the problems interesting. And this explosion sort of happened in the later 1990s and into 2000 when networks became a big thing and mobile communication became a big thing. And all of a sudden, now we have so much data, and not data about machines, but data about people. And that sort of completely transformed the way I was thinking about a lot of the problems we were working on. But the genesis of a lot of that work was actually happening in the control community in the early 1990s.
I guess also in one way or another in relation to the line of research connected to adaptive control, because that's very much in line with merging learning algorithms with decisions, taking optimal decisions. I hope we can talk about it also later, because we exchanged also briefly via email a nice book that is going to come out soon, Data Systems and Society. Short advertisement, because it's absolutely worth it. It will be, amazing to those who read it. At least I really enjoyed reading parts of it. I have lots of comments there.
Yeah, it'd be nice to talk about that. And the book will be out in April 2025, but it is already in press. And it is a non-technical book. And it is trying to bring together the philosophy that you learn from control theory into how it actually interacts with statistics and interacts with information theory, interacts with network theory, but all for societal problems. And yes, we can talk about it later, but I just wanted to make a comment that I think it's really critical as we think about control theory. It's really about societal problems. We flying and going to space and so forth, but we abstracted away the society from them. And then what has happened in the last, I would say, decade is that we're bringing back the society into the problem, which is changing, first of all, adding so many interesting problems for the researchers, and also changing the impact that the control theory community is having.
I absolutely resonate with this. In fact, I really love the quote that you have in your book. I think towards the end, there's someone else from humanities saying, engineers and computer scientists look for technology to solve problems. In humanities and social sciences, these solutions are perceived as the problems.
Yeah.
Which is, it's great. We're definitely going to talk about that. Maybe moving chronologically. So you're now at MIT, and we're situated in time around 2000s. And I believe that you hired a student together with Eric Ferron called Emilio Frazzoli. Is that right?
That's correct.
Okay. So I don't know how the topic of his PhD emerged. That's essentially in the realm of autonomy, motion planning, how to maneuver agile robots and vehicles, let's say, in different ways. I wanted to talk about two publications that piqued my interest. One is Real-Time Motion Planning for Agile Autonomous Vehicles, and the other one called Maneuver-Based Motion Planning for Nonlinear Systems with Symmetries. I was wondering, how did this topic somehow stimulated your interest, and how did you came up with the solutions you came up with?
So I'm going to make a specific comment I'm going to make a general comment and a specific comment. So the general comment I would say is that, and I can absolutely say this with all confidence, that throughout my whole career, it was my students who took me from one problem to the next problem. I have a style of working with students, which when they come in, I always tell them that formulating your PhD problem is 60% of the PhD problem. So I'm not going to tell you what to do. You got to tell me what you want to do. And they explore, and we talk, and we interact, and so forth. And through that process, I have moved into areas that I would never have done on my own. It would be impossible for me to actually have explored these areas on my own. And so that's a general comment. It's true about every piece of work that I've done. And if you notice, I have bodies of work, and they're centered around usually a couple of my PhD students, and it's been just kind of a journey of hopping around in different problems. Of course, there are things that you don't see, and those are the problems I wasn't interested in, and maybe indirectly kind of, steered the student away from them. But there is definitely a lot that have to be given to the student for finding these directions. On the specific of the work with Eric and Emilio, I have started working with Eric before that, and we had another PhD student, actually two PhD students, who were interested in looking at robust maneuvers around equilibrium surfaces. So we came up with this idea of overlapping Lyapunov functions and sort of moving from one region of convergence to another region of convergence, allowing a trajectory to be robust along, say, a trim surface of an equilibrium surface. So we have had those publications before. So when Emilio came, I think the question has become, so how do we do complex maneuvers? So these are just trim surfaces, but what about, transitioning from one equilibrium trajectory to another equilibrium trajectory? You think of a helicopter, for example, in a hover position, that's equilibrium, wanting to move from that position to a right turn. The right turn itself is an equilibrium trajectory, but the transition is not, right? And suppose it wants to do that in a sort of a aggressive maneuver, fast and in an adverse environment and so forth. So we began to think about this bigger, higher level problem, which is maneuvers that are not all equilibrium and transitions between them. And how do we guarantee that, in fact, we can come up with an architecture which is provably stable, robustly provably stable, right? And so that's sort of what intrigued me to think about these types of problems and the interaction with Eric and Emilio. And of course, I give all the credit to Emilio for doing all the work, but this sort of problem was actually exciting from that perspective. And so then we started thinking, okay, of this robust hybrid automaton architecture, which is really at the core state of each, the core state of the automaton are trajectories that are stable trajectories. And then the automaton describes the transitions among these things. And there are also finite time optimal control problems that are supposedly going to be robust in the transition from one state to another state. So we came up with this consistent architecture. And then we showed, for example, with flight problems like helicopters and so forth, how the symmetry allows us to characterize all of these trajectories with only very few primitive trajectories and generate all of this dictionary of possible complex interactions with very few trim trajectories and then expansions among them. I thought the work was really exciting, and it was great time working with both Eric and Emilio. It's one of the highlights of my career in terms of interactions with students and colleagues. And Eric was a great collaborator as well, I have to say, because also Eric was building things. So he built, for example, about a 1.5 meter long autonomous helicopter, and we were doing a lot of testing on that. I was not a builder. So Eric was building these things and testing them out there, and we're generating hypotheses from the test experiments that Eric was doing. And so it was kind of a very fruitful and exciting collaboration.
I should also mention for the audience that Eric Ferron is also very well known in our community for basically writing this book on linear matrix inequalities, on top of many other things that he's been developing. I particularly found very interesting, as you mentioned, this notion of the maneuver automaton in this paper, which essentially is an abstraction of the physical object that we are trying to control. And as you say, we use symmetries of the system, for example, in this context of an helicopter, to devise motion primitives, which are using, I would say, reachability analysis, allow you to move from one state to the other. It's certainly a very fascinating subject. I was not aware of it, and I'm glad that in preparing this episode, I managed to read this paper as well. Strongly recommend it to the audience.
I'm amazed how much work you've done on this. I mean, you've actually dove through the papers. And in fact, I mean, that's actually a very good point that you make. And the other thing is, of course, once you characterize this hybrid automaton, now you pop the problem into a trajectory planning problem. You see, and all the stability and the robustness is taken care of at the lower level. So this hierarchical structure allows you to do kind of optimization at the very high level, and then it gets translated down into sort of robust strategy. It was really interesting. And of course, as you know, Emilio moved on to develop a lot of these ideas further. And then he was the founder of Newtonomy, which is one of the very first autonomous vehicles cars that actually was tested here in the Pier area in Boston. And so it's very amazing and successful trajectory for Emilio. And of course, I would say a lot of that started in these types of works, and thinking about these types of problems.
And still seems to be very relevant today. I mean, this concept of abstraction, we talked about it also with other guests, for example, Alberto San Giovanni Vincentelli, where you may intentionally actually abstract a physical system of which you do have knowledge, but for different purposes, for example, planning. very interesting line of research per se, let's say.
I would say that maybe we'll come back to this when we talk about societal challenges. Also, I do have a full chapter in my book about the power of abstractions.
Indeed.
And I think, as you said, I think it's one of the amazing things that we do well as engineers, but we don't know how to teach it. And it's something that we should ponder upon and think about. Yeah.
That was actually my number one. I want to take this tangent, allow myself to go on this tangent, because obviously we continue to talk about the book. We'll get there eventually. But this was really the first note that I made about the book. So in somewhere as you say, in I think chapter 5, maybe, when you talk about abstractions and how good we are also at developing abstractions, at some point you have a strong statement that says, I contend that there is no systematic approach to deriving an abstraction. Instead, in my view, it is a manifestation of creativity and of our minds, which is, at least to me, I made the association with something that I read in one of the 1986 papers from Willems himself, because he was also thinking about how do we create models of dynamical systems. And in, I think, paper part 2, he has this famous quote, or famous to those who have read it at least, saying models are a matter of inspiration, not of deduction, which I found very much in line with what you were mentioning.
I felt really bad reading your comment that I actually didn't know this quote. You forget what you read, and I feel bad now because it's too late for me to include it in the book, but it would have been a perfect statement for what I was saying.
Yeah, I mean, I've been thinking about these subjects myself for a little bit in the past year or so. Obviously, Willems had in mind the concept of falsification coming from his own endeavors in dealing with time series and constructing dynamical system models from time series. And he considered obviously induction, deduction, and then inspiration. And he claims that at the end of the day, what humans do is create models from inspiration. You cannot deduce them, and you cannot create models from induction. Black swans being one example. So I was actually curious to hear your opinion about the power of abstraction and why there is no systematic way of creating abstractions.
I think that everyone has a certain view of what they mean by abstractions. You see, that's one of the issues that I found interesting, is that I couldn't define what I wanted to say about abstractions. I couldn't define what abstractions are. I used the Netflix series as an example of how, when you draw a simple heart in pink or red, you're actually representing that there's a certain emotion. But if you drew the details of the heart with the veins and so forth, I don't think it portrays emotions, right? It looks like someone who has a heart problem, right? And so it's this sort of level by which you project something and it makes sense to you. It creates a certain reaction to. So couldn't define abstractions, right? So sometimes abstractions are approximations, where you kind of get rid of things and you focus on a few aspects of the system or the problem or the phenomenon you're looking at. And that's reasonable if what you got rid of really can be gotten rid of, right? I mean, or that what you retained is enough for you to develop the right intuition and the inspiration. Sometimes abstractions are very different than approximation. They're not even approximation. They don't even try to approximate, but they try to give you a sense of what you're looking at and so forth. It's not always the same. Now, I do use in the book, and I also in my classes, various approximations / abstractions that I think have been extremely powerful. From the controls community perspective, we have the whole idea of the equilibrium as a notion of abstraction. And that's also applied in economics. The general equilibrium theory is a way of thinking about how certain subsystems interact and sort of cause other systems to settle in certain places and so forth. You can argue that no system exists in equilibrium, or very few systems exist in equilibrium on their own, but maybe for a short period of time. And it allows us to think how to design such system. We think of equilibrium as designing airplanes. We want to simplify, not complicate the dynamics of a system. We want to settle them on an equilibrium that we know that they're predictive and we know exactly what's going to come out of them. But then I use examples like Shannon's theory as a very interesting abstraction where, in a way, in almost every aspect of it, it did not represent reality. But yet has been the underlying power of all digital communication that we see today. And that's an abstraction it was brilliant. It was hard to understand how he came up with it. Kind of got rid of time, got rid of all sorts of stuff that are really necessary for a correct communication system, a real-time communication system. But focus on the issue of capacity and how you actually utilize a channel in the best possible rate you can. And, we're not getting into that. So these are examples of different kinds of abstractions. And the reason I'm mentioning them in the context of society, you see, and the reason I was thinking about that a lot is that the tendency that you see in a lot of fields to model human interaction with machines as what I call enterprise model. An enterprise model is basically you have a model of a machine and then you have a complicated network of people. You model that. And I don't know, you have some other parameters and system operators. You model that and you put them all together. You put them all together and you start simulating. And I'm saying, in general, I don't know, this could yield something for you. But for me, it adds nothing to my knowledge or my ability to understand this interaction.
Yeah.
This is an enterprise type model. It's not really good for research and it's not good for building confidence that you really understand this interaction. Mm-hmm. So what's lacking is the abstraction. What is the essential piece of the interaction between the people and the system, right? Mm-hmm. The people in the system. What's the essential piece of this interaction? And that abstraction, it's challenging because the nature of these things are very different. One is coming from physics, biology, chemistry, blah, something. We build a system or even fixed protocols or fixed structure. And then there's humans who are reacting sometimes in a particular way that we have to model and understand. And it's the absence of these abstractions that have made it difficult for us to understand these sort of black swan phenomena when you have the interaction between peoples and systems. But that we need to think about them. The power of thinking about these things, and then there are, rational theory in economics allows us certain types of abstraction. Say, if everyone acted in a rational way, then this is the kind of thing to expect. And then you got behavioral economics that tells you, okay, actually sometimes it's not about rationality, it's about nudging people to think in a certain way and so forth. These are abstractions that are very helpful. But these are done separately from machines. And now what we're talking about, how do people interact with systems? Now, how do we abstract the two together to think about this problem in a very interesting way? So I give you an example that is emerging in artificial intelligence right now. And we talked a little bit about that in the podcast at the ACC, right?
Yeah.
And it's an example that emerged from a conversation I was having with Jeff Shamma a while back. And it really is interesting, and it was motivated by thinking about TikTok.
Okay.
I mean, you think about TikTok is an AI agent. It's collecting data about you, and it's learning, and it's providing you with things to look at. And as you look at things, it collects data about you. But it's adapting to your behavior. It's adapting, it's learning about you. That's a system. However, you as a person are also adapting to the TikTok. You're not stagnant. You are also adapting and you're changing. Both of you are learning from each other. The algorithm that runs TikTok is probably something written in a computer somewhere. But your algorithm, we don't understand. We may think, okay, what is it that you want to explore? What are you trying to get out of the TikTok? Now imagine that you have communities of people who are networked, who are using these agents. What sort of equilibrium do you expect to see out of these people that will tell you something about the final effect of TikTok on people's behavior? It's a complicated problem, right? And so it requires to solve these types, and this is just an example as we have more and more AI agents roaming the universe that we live in and interacting with us, and we are reacting to them. I have a funny story about this because a few months ago, I had my first shouting match against a chat bot.
Shouting? Okay. I was wondering whether I understood correctly.
I'm typically a very calm person. I don't shout, and certainly not with people on the other side. But the chatbot, because my internet broke, and I was trying to contact Xfinity, the provider, and I kept going to a chatbot, and the chatbot is not allowing me to explain what has happened. It has limit, and I've tried multiple ways, and every time I end up exiting the system and I have to re-enter, and I go through the same process, and I lost my temper. And I started thinking to myself, this is really amazing. This is a technique, losing your temper, that doesn't work with the chatbot. I had to calm myself, drink a few shots of espresso, and then come back and deal with that situation. But it's just an anecdote to say that these are systems that are roaming our world, and they are going to affect us and affect our behavior. And this human system interaction is really fascinating and complicated in many different ways. And I think some people are doing a good job thinking about pieces of that, and that's sort of the progress of research.
It's definitely surfacing, I would say. I saw it also in the manifesto. I forget the specific name of the Control Systems Society document that has been put forward a couple of years ago, I think, about cyber physical systems with humans in the loop. We started this tangent actually talking about abstractions and the power of abstractions. I find all of the topics that you touched on fascinating, but I'll try to bring us back to 2004 chronologically, where we were. And then I think we'll gradually eventually get to talk about these issues. I mean, certainly one by one. The other authors of another Axel V Award paper will not be angry against me if we gently skim through it. I'm talking about distributed control of spatially invariant systems, a delightful paper, joy to read. We talked about it actually in the episode with Bassam Bamier, and therefore I propose to jump forward in time just because there's so much to talk about, and I will refer the audience to that. Delightful read, fantastic ideas, all related also to this concept of architecture. But I would say, something that really struck me in analyzing your trajectory, if you want, over time, was that there was a recurring topic coming up all the time, and that's the notion of causality. Causality seems to pervade your research at every level in time, let's say. There's also some excerpts in your Data Systems Society book that I would like to read. One is Causality from Observational Data is the holy grail of statistics, and one that has a profound impact on how we explain data. The reason why I bring it up now is that I think this is also very much related to another pair of publications that in 2008 and 2010 get respectively the Hugo Schuck Award for Theory, and the following journal paper version, the Axel V Award with Nuno Martins, that essentially deal with feedback control in the presence of noisy channels, whereby you give essentially fundamental limitations, Bode-like formulas for feedback systems affected by noise. I will let you maybe explain the relevance of this research, just because I want to do justice to it.
Thanks. Well, I think that the some of the work, we've been thinking about the control theory in context of other existing systems. And one of these things is, how does control fit within communication systems? And so when you think about the Mars rover, what you're doing, you're controlling something that is far away, and the communication channel matters. It matters a lot, right? Now, in the past, one could say, because the distance and the travel time for light and for signals isn't that much, communication can be just represented by noise. That would be enough, right? But then if you're dealing with something that is so far away, you have to start thinking about encoding and decoding the signal. And if you're encoding and decoding the signal, the channel encoding and decoding, so that you can transmit the signal in the best possible way with a very small probability of error, this channel becomes highly nonlinear and complicated. And then the question is, how much do we, and so there was some previous work that was pioneered by Sergio Mitter and his students to talk about sort of what are the stability limitations when you have the encoder and decoder. So you can imagine encoding and decoding essentially adds substantial amount of delay in the channel. And that delay then has the ability to destabilize the system. But I think that sort of was interesting, but it didn't come to the essence, or at least it provided us with step one towards the real question that we often ask about in any control problem, which is how much performance can we get out of it, right? I mean, at the end, we design a control system not just to stabilize, although stability is really critical, but to also get certain performance. And now we wanted to understand what are the performance limitations of having to perform this encoding, decoding, say, in an optimal setting. What are the performance limitations? And in particular, a lot of, if you go back to the earlier work of John Doyle and Keith Glover and so forth about loop shaping, right? I mean, we understood a lot of the robust control when we were able to apply them to both the integrals formula and different types of limitation characteristics, right? Some conservation laws that say, well, you can't really get performance across all of the frequencies, or those were very intuitive type of limitations of controller design that allowed us to design loop shapes that are viable, and we got good control. At the end, H infinity wasn't just the only way to design a system. You needed to think about how do you pick the weights and how do you use the technology to give you controllers that you like. So in the same vein, how do we do the same thing when we have now these communication constraints? And so our idea was, so what is the limitation that is given by having a finite capacity channel? How does that limit the trade-off of a body integral formula? And so we wanted to kind of connect all of this work to the loop shaping work by providing new inequalities for conservation inequalities for a closed loop control system. And that was the significance of Nunu's work in this area, which was also really interesting and different than just analyzing the stability problem.
Fantastic work. At least I personally really enjoyed reading this line of research. I guess, just for the audience to provide some intuition, what is going on here, as you mentioned, there is noise affecting a feedback control system, and the fact that we're able to characterize some Bode type kind of integral formulas, conservation laws, in this case on the information actually that goes across the channel, essentially gives us a way to quantify performance limitations of the particular feedback control systems at hand. And in this sense, the key insight is that feedback cannot fully cancel the effect of noise.
That's correct.
That's what I got out of this.
Correct.
Also, as a very nice tangent, I found that as a follow-up of this particularly theoretical result, there is a follow-up paper that essentially applies these ideas by Ioannis Lestas, Glenn Binnicombe, and Paulson from Harvard University that uses then these results to characterize fundamental limits on the suppression of molecular fluctuations. So there, the authors essentially look at negative feedback mechanisms that are stabilizing certain biological processes at molecular level, whereby noise actually matters. And they show that essentially cells need to compensate for the fact that they're inaccurate in, for example, signaling events by doing that more and more times, basically tens of thousands of times per cell cycle. And at least to my knowledge, the philosophy seems very much the same, that the results seem very much in line, if you want, with the paper that we are discussing now.
That's a very good point. And I think that also the insight that you gave to think about control theory as a way of information transfer. And that was, I would say, present in the work of Sanjoy Mitter and his students, and also Nicola Ilya and Sanjoy, and sort of the whole idea of thinking, in a way, we start thinking of feedback control as information transfer, which I think Nicola also have taken that work into how to design channel encoders and decoders using control theory. So kind of this whole connection between information theory and control theory in this body of work with a lot of people has actually been quite interesting body of work. And to what extent actually information theorists, or what do you call them, communication really system, have used that sort of feedback stuff, I'm not sure, but this application that you described with Glenn, I think, is another example.
Amazing. So now, at least according to my notes, we're situated around 2010s, more or less, in time. And this is really what I dubbed in my notes, at least, as really the era where data systems and society topics take over in your research. There's a number of publications that I would like to mention in this context, but I'd like to think about this phase transition in your research journey as focusing now on, as control theorists, we always think about closing into a certain box certain systems. And now some systems of interest or that seem to become of interest to you are markets, for example. So the actual economics that drives behavior and the data that one can actually measure, particularly observational data, for example, from human behavior, but also different types of data like prices, for example, in power grids. I've noted down a number of applications. I don't know, I'll let you choose actually which one resonates with you best. I have one that is titled Bayesian learning in social networks, but also volatility of power grids and the real-time pricing. I don't know, what would you like to talk about next?
Okay, so I think I want to talk about Bayesian networks, but let me make a comment about the power grid.
Sure.
Just as an anecdote. So as I said, the majority of all the work that I've done has been primarily one way or another sort of a chance that led by my students and my conversations, not pre-planned. This is the only area that was pre-planned.
Okay.
You know, and it was interesting because around 2005, 2006, we started conversations in our Laboratory for Information and Decision Systems at MIT, that renewable energy is going to come really fast. And in particular, for example, we're going to see a lot of electric vehicles, a lot of different sources of energy. And the challenges for that problem, because of the uncertainty in generation, the uncertainty of production and all of that, brings up really interesting problems and one that we should start thinking about right away. And so we started thinking about the smart grid, power grid, which of course, rethinking about the markets, rethinking about EV, charging, all of that stuff at once, right? But I have the completion of this anecdote to say, hey, however, I've actually been incredibly disappointed by the growth of renewable energy in the United States. I mean, we are nowhere. I was literally thinking 2007 that within 5 years, 10 years at most, more than 50% of the cars will be electric cars. And that we will have different types of systems running. But, you know, you go around the United States right now, yes, you see a lot of Teslas in the East Coast and the West Coast, but it's not the same level of penetration. It's not the same change in the way systems are operating. It's coming, but it's coming a lot slower.
Why do you think it's coming so slowly? Sorry if I interrupt.
I think this is an interesting economic question. I think in the United States, we have a very strong car culture. Mm-hmm. And in particular, I think with cars that don't have high range, it was just impossible for families to. So we don't accept the idea of renting a car when you need to travel. So this dual use where you have a small electric car in the city, but then if you need to go somewhere like 500 miles, you might as well rent the car for that period. It would be a lot cheaper for you than having a large SUV parked in your garage. But the culture in the United States is not that. You know, I think people love their cars and their big cars. We have a lot of big cars in small towns, which is really amazing, you know, kind of a thing. That's one advantage, one issue. I think the range is solving that problem. I think the fact that the car range is going higher and higher. We've been very slow in building the infrastructure.
I was about to ask, actually, this would be my first guess. Do you think that's a matter of infrastructure?
It's infrastructure. Again, it's a feedback system, right? You know, if people were jumping on cars, we would have built infrastructure, but people were not. So there's kind of a, I don't know, the leader and the follower there. But right now, you know, for me, and I have an electric car and its range is about 270 miles, which if I wanted to go from Boston to New York, which is about 200 miles, it's okay, it gets me there, but it doesn't get me to a station where I can charge it. And so I have to find a charger in the way so that I can come back to the charger in the way. And to do that, it's a disruption. It really is not that obvious where I can stop. It's not like every gas station has a charger, and especially superchargers where I can get it in less than half an hour. So it's a deterrent, right? If you take these kind of trips often, you would be thinking twice about whether this is the kind of car. So the infrastructure has really played an important role. I think part of the decentralization of states' ownership of power generation has also contributed to this issue. A lot of different reasons, honestly. And we are seeing better acceleration now, thinking about more coordinated efforts among generation, in particular after what happened in Texas when the gas froze because of unexpected temperatures, and we had an outage for over 24 hours. And that was a couple of years ago. It was a major disaster, really, to think about a whole state kind of sort of going out of power and not be prepared for these kind of risks. So I think we're beginning to think a little bit more systemically about how these problems are done. But anyway, so it's just that the anecdote is that I wish that things were different, but that was one research where we started getting together and talking about what problems should be tackled in that space.
Yeah, that's a paper that you wrote with Davi
Madhavich,
Chehani and Sanjay Mitter.
Sanjay Mitter
right?
is about volatility of when you have elasticity in the market. But, I wrote multiple papers on systemic risk. We can talk about that. But I am actually, let me talk about Bayesian networks, which is a paper that I wrote with Daron Asimoglu, Seward Dörfler, and our student Ilan Lobel. And of course, as you all know, Daron just recently received the Nobel Prize in Economics and on his amazing work that he's done on why nations fail, plus some other works from before. And it's been a tremendous experience working with him on this particular line of research. And as well as, of course, interacting with the rest of my colleagues and my student, Ilan. And it was a nice piece of work because I, at that point, was only marginally working on social networks. I haven't really there was a social networks research topic that has emerged, and people were looking at consensus networks and different types of convergence arguments and so forth. But the problem we were looking at was a question of how information cascades among networks, and so the real-time aspect of this. And in particular, kind of a really interesting fundamental question. If you think about the law of large numbers, if I am getting noisy information about a parameter of some sort, about a concept, a parameter, and I'm getting noisy information, but the noise has a little bit, it's not obfuscating the signal completely. The law of large number tells me if I get infinite of those, I get that parameter. This is sort of like the averaging or the sort of basic principle behind why uncorrelated noise can be gotten rid of. You average it out and it goes away. So now imagine that this infinite amount of information, finite going to infinity, is not arriving to one agent, but arriving to multiple agents. Each agent is getting one signal, but these agents are connected on a network. Can we aggregate that information to actually get consistency in the limit? So in other words, do we learn as a group? We learn as individuals if we get all the information for that individual, but do we learn as a group? Well, the idea is the group, if they are in the context of decision-making, they don't communicate the signal that they get, but rather they communicate the decision that they made. So one example would be, we are on a social network, we are on Facebook, and we are trying to buy the next computer, okay? And so each one of us is getting some marketing information about that computer. I call that independent marketing information. It's useful information. So I want to get a Mac. It says it's fast. Somebody says, okay, yes, it's fast, but it heats up too quickly. Somebody says it's convenient. So, some of the information you get may say, oh, I'm not going to buy. Some of the information I get says, oh, I think I'm going to buy. And then we communicate this information, and then the next person sees some group that either bought or didn't buy, right? The group may not be everybody, so it depends on their network. So there's a network structure. And then they get their own independent information that tells them, okay, actually, it's cheap or something like that. So it's also marketable. So how do they aggregate? They aggregate that information, say, through a Bayesian thinking. I have this observation of what other people have done, plus the independent information I have, and now I make a decision, and now that decision is available to the next group of people. So we ask the question, do we actually learn whether it's a good computer or not? And the answer is most of the time you don't. And that's the sort of the idea, is that learning on a network, unless the network is structured in a very clear way, the network changes the aggregation of information. And that was really interesting for me. It's kind of like this piece of work was the opener of thinking about what networks are all about. It's not about that there is this whole work that talks about belief propagation and learning on networks and so forth. When these networks are agents that we design, a lot of that work made a lot of sense. But when you think of the network as people, and they're not agents you design, you start thinking of the network as a constraint on the propagation of information. And that kind of began to start sort of shaping my thinking about networks interacting with systems. There's an information flow, but the information flow is constrained by the human networks differently the way it's constrained by physical networks that we can design. So I really liked that piece of work, and it was really a change of mentality for me in terms of how I think about social networks and social behavior, and later on in terms of questions about systemic risk, in the sense that systemic risk is also caused by cascaded information, by cascaded of decision, right? So it shaped a lot of the work that I was doing afterwards in that regard.
Amazing. I guess maybe my understanding of this paper is that network structure deeply influences learning outcomes, as you in the setup that you just described. And in fact, I mean, it seems like this topic really piqued your interest, because then, I mean, I see also other related publications that go in this direction. I'm thinking, for example, the 2015 two-part paper on robust distributed routing in dynamical networks. In a way, this is related, as you say, to the concept of cascaded failures and how to prevent them in a certain sense.
Yeah, that piece of work, just a comment on it, is that, as I say, I'm shifting now, you can imagine, I'm shifting now in my thinking towards how social decisions affect physical systems. So that's the interaction that I was thinking about. And so that work will also add to the group, Giacomo Como, and Ketan Savla, and Daron Asimoglu. This work has, and then later on with Emilio as well, is to try to understand cascaded failures as a result of human decisions, not as a result of just natural congestion, because, and then understanding the margins, how the human decisions change the robustness margins of the physical system.
I find it amazing as you are thinking that, I mean, I can really see how robust control philosophy pervades much of your thinking, because you're talking about margins, and I understand what you're trying to say. Also the performance, the failures are...
I think that, as I said at the beginning, it looks like different work, but it was all about decision theory. It's not that different. Once a control theorist, always a control theorist. You can't escape.
It's amazing how, I mean, going back to the power of abstractions, it's amazing how those abstractions under very limited assumptions like linearity, time invariance of certain systems can be extrapolated in contexts that are so different and where these assumptions certainly do not hold.
It's true. And something that we haven't talked about, which is how much I enjoy teaching. And I'm not saying I'm a good teacher, but I enjoy teaching. Those are two different things. For many years, I taught the introduction class in system theory at MIT. And it primarily was linear system theory, robust control, robust systems, and so forth. And every time I remind them that none of this is about linearity. None of it is about linearity. But I can give you complete answers in the case of linear systems. That's all. I can give you the answers in the case of linear system. And it's important that you know that there are examples out there where there are some clean, elegant answers. Not everything is completely simulation-based or computationally based. There are things that have structures. And when you understand the structure, a lot of stuff simplifies. Computation simplifies, intuition comes through, and so forth. But the concepts, as you can see, really has nothing to do with linearity or a particular type of models that you have. And that's actually, again, as I said, and it was maybe Carl Astrom that has been saying a lot of that stuff, is that we don't really explain control theory very well to other people. I go to the extreme point of saying that actually we try to obfuscate it as much as we can, but not intentionally, sort of just unintentionally, myself included. I'm not saying I've done a great job doing that, but we understand that it has that ability to be expansive as a field. Yeah,
indeed. So at this stage, I have maybe two ideas about how to move forward. One would be to dig deeper into this 2015 paper that we just mentioned on distributed routing. And then as a follow-up, maybe, or if you want, think about how the creation of the Institute for Data Systems and Society has shaped also your thinking, because I think in time, at least we're situated around in a neighborhood of these years, right? When did that happen?
So in 2013,
Yeah.
I was asked to put together a committee to think about creating such an institute at MIT. And it was launched officially in 2015.
Okay, so we really are in time situated there.
Yeah.
Maybe, do you want to talk about that maybe, and then we can go back to the paper?
Yes,
Or,
yes, of
as
course.
you wish.
I'm flexible. I can talk about that. It was a big part of my life, launching this particular institute. It was very exciting, and it was a recognition by MIT at that time that things are changing very rapidly. That, of course, we have seen the explosion of data, and we have seen also the improvement of computational power. And we began to see what I refer to as the fourth revolution of computation in my book, which is the embedded systems and sort of AI systems, essentially AI systems sort of present everywhere. And we needed to understand, at the MIT perspective, of course, it's not so much to say, oh, this is the institute that will do the work. I mean, MIT as a whole does everything. But that where is a place where we can begin to think about the challenges, the societal challenges that are coming from different domains, but that are requiring data and systems, otherwise AI, as a way to solve them. So we began the deliberations. And what was interesting about that is just a few characteristics. There were 40 people in that committee. And I joke around a lot to say that when I came up with 40 people to the dean and the provost, they were laughing, saying that I'm trying to kill the project. Because it's practically impossible to have 40 faculty, let alone 40 MIT faculty to agree. I mean, you can get 2 people to agree. I'm happy to say that the proposal we made was supported by 38 out of the 40. And there were 2 dissensions, which also had good points about why they did not agree. And so then there was the task of actually and what is the important things? Of course, we came up with what I call the triangle as the basis for understanding the mission of this particular institute. And the triangle is really simple, but it's actually also, in my opinion, quite powerful. Complexity in societal problems maybe can be broken down into the interaction of 3 pieces. One piece is the physical structure, which is often dictated by either physics, chemistry, biology, or protocols like a financial system, or the systems that are systems. It's this, computer scientists call that systems, we call it system theory, doesn't matter. Then there is the how people interacting with that system. And then there are the institutions interacting with that system, institutions being governments and markets and so forth interacting. Markets and governments are different than people, and they are all interacting with each other. And so you can think about, in my book, I give a lot of examples with these things. COVID-19 was a beautiful example of this, and came and hit us right at the middle of our building of the institute. COVID-19 was an example of this triangle, the physical aspect of the virus and its transmission and so forth, people interaction and their network and their contagion effect, and then the institutions in terms of rules of lockdown and the masking and later on vaccination and so forth, and testing and then later on vaccination. And then you have connecting all of these pieces, a lot of data that you measure. And the data that you measure is not uniform, it's not the same. Data that you measure on the system level is very different than human behavior, which you can only observe from a higher level, and very different in time scale to the institutional data of, say, regulation and policy and so forth. So the timing of all of this is very different. The nature of the data is very different. And now we're trying to make decisions. We may have models of the physical process. We may develop some models of human behavior. We understand some objectives of how governments and institutions are making decisions. Or we are probably the decisions we're trying to make are the policy decisions that the institutions are trying to make. So how do we understand this interactive diagram with data? And in the COVID-19, what was actually even emphasizing the concept of robustness and learning is that the data wasn't available all at once. That at the beginning, when we started, we didn't have enough data. It was just very sparse. But people are asking for decisions. And you have to make some decisions. You can't just say, oh, sorry, wait until I have an asymptotic convergence argument, and then I can give you some decisions. And some of the decisions you make at the beginning may be wrong. That's again, this criticism, oh, you change your mind. Well, science is not stagnant. Science evolves, right? And we may make a wrong decision and come back and say, no, sorry. Like I would say, one of the biggest criticism that happened with COVID-19 is this idea that in the United States, when Fauci came and said, we don't need masks at the beginning. And that is a decision, of course, there's no medical worker will ever say you don't need a mask, because a mask can at least prevent something. It may not be that effective, but it's not going to hurt you. But the reason they said we don't need masks is that first, they didn't understand exactly the impact of masking. And two, we didn't have enough masks. And so that would have depleted the masks from hospitals where they were needed the most. So it was an economic plus medical decision. Then things change and we change the decision. So this is a complicated thing and it evolves. And just because you don't have all the data doesn't mean you don't make decisions. But this is this picture, this triangle. You can apply it, transportation systems, people, regulations, system. And this triangle tells you also the kind of thing that you have to learn to tackle these problems. And I call it the trilingual student, that are experts in these different components and experts in data science and statistics, that they understand how to use the data to kind of connect the dots in all of these problems. But none of this would work if you don't develop the right abstraction for the problem. And then we've seen abstractions for the COVID-19. We've seen abstractions for transportation systems and what have you. So the triangle brought everything together for us. It was a really nice story, because now what we're saying is that what do we need in terms of academic programs? We call it the trilingual student. So how do we educate students in the right technical fields and social sciences so that they are able to embody this understanding of what people do and what machines do and so forth? How do we educate students in terms of statistics so that they understand the data and so forth? And that's how we built our academic programs. It's how we hired our faculty. It's how we supported research. It was a story that came from a vision, and this vision was captured in a triangle. And it was really exciting to see the learning curve that all of us were going through. I have to say that I've never in my life talked to as many social science and humanity faculty in my career at MIT, understood the kind of problems they're working on and how they're approaching it and what their philosophy is as they tackle these types of questions. In fact, I always joked when I would go around giving talks with locally and outside, I would say, in my first 25-year career, I actually never cared about people. They were not in my form. They were not in my research. In research, I cared about people outside research. But in research, I didn't care about people. They were not factoring into my formulations. And even though we thought about human in the loop and so forth, we didn't think about it as people, as social phenomenon interacting and so forth. And that changed the way I think about it. And I changed the way, and I still don't think actually I have a way of formulating the kind of problems we want to solve. Because as engineers, we rely a lot on utilitarian definitions.
You do talk about it actually in the book.
Quite a bit.
In describing now the founding of this institute, you also gave a wonderful preview of your book that will come out in April 2025, which describes essentially this journey.
Exactly.
And yeah, I found it very fascinating book, strongly recommended to the audience because first of all, it has no equations to the best of my knowledge. I went through it and it was a bit of a surprise.
No equations.
But also it deals with everything that we just talked about now, and I guess we will also continue later.
I really enjoyed writing the book. And so just to finish that thought, I would say that the utilitarian definition of things doesn't always cater to the needs of every groups of people in our society. And that's, I think, really a problem that we need to be careful about. And that's what kind of induces the systemic racism and systemic types of bias, right? Because Well, certain people are not factored in our equation, and they don't matter that much in our equations, but then in real life they do. And they have a huge impact. And it's an important aspect of this. And as I talk about, for example, credit scores for lending money and so forth, I mean, all of these things, I understand, of course, banks want to protect themselves and they want their loans to be paid back. But there needs to be other ways in which we understand for people who were not in positions to be competitive in these types of kind of metrics, how to bring them along, a process of bringing them along. And so I go a lot into that quite a bit. But I didn't enjoy writing this book, just to comment back and say, and it was a culmination of what I learned over the years, but also in particular the last 8 years or 10 years now with IDSS. And I was thinking to myself, I don't know, there's a bit of a story there, because I started writing during the pandemic. And, you know, I think a lot of us, different people, we all reacted differently for the pandemic, right, in the lockdown. I mean, some people got pets and some people, I don't know, you know, it's just like we started cooking every day and I don't know, everybody. And I started thinking, it's interesting that when you write it, when you work on research, you write a paper. So you leave a trail. Sometimes it's not even a good paper, but you leave a trail. It's a trail about you thought about this. And sometimes a bad paper, or not a bad paper, but a paper that you still not convinced that you got what you want out of. You still write it. And then maybe not published, maybe in your archive and so forth, but it kind of works as a trail. And then later on either you say, oh, student, look at this, I tried this and it never worked. But when you do this type of administrative work, which you build in a unit, or people typically don't write papers about this. And so there are experiences to be shared, and maybe for some other person who's trying to do a similar thing, or maybe for a student who's going to be in that kind of a program, or a student who's going to be in a different program. And so the motivation for me to write came from having a little bit of time during the pandemic and thinking I probably stepped down from the directorship right after the pandemic, and then I'll go do something else. And then what? And then I probably may not have the opportunity to share the experience I had in doing this. And so I started writing. And it was enjoyable to see myself, to see kind of putting this together in a way. And also I have another story there.
Please go. I'm glad you did, by the way. I'm glad you did take the time, because it's a very interesting book to read.
So Alberto, I will tell you this, okay? So first I started writing and I was boring myself. Okay. I hated what I wrote. I hated it. I'm writing and I'm putting hours. It's not like I'm not putting the hours, but I'm not seeing it coming through. And it was interesting, you know, I've just never written something like this. The largest maybe piece that I would write is a page or something, a page and a half, you know. Now, there was a very important person here that I contacted. It's a person that I met through some other dealing at MIT, and he's a science writer. He's a great guy, Robert. And so I contacted him and I said, look, I have this project. I'm trying to figure out how to write this thing, but it's not coming through, and I want to write it to a broad community, many of them will be students for sure, but many people who are also in their careers, and maybe people who may want to build something in the future, not this, but something else, but they will learn things experience. Anyway, so now I'll make a long story short. First, he helped me sort of put the table of content together, and that was really interesting. You know, how do you organize your thoughts? And there was several months working on just what are the building blocks and what are the anchors of the book. And that was really interesting for me, that I don't do this often when I write a paper. Somehow the anchors are automatically figured out for us. That's maybe one reason, or I just don't think about it, and maybe the paper could have been written better that way. But somehow we write papers to each other, and because we write them to each other, we forgive each other for not being clear, you know, because we know each other and we know that we can do that. We can plow through it. But when you write to a broader audience, it's a different story, right? And you can't assume what they know, what they don't know. So the first thing was the table of content. And then I would write something and I would send it to Robert, and Robert would come back and give me some feedback. And he's a super, super nice guy, right? So I think he's a very diplomatic and everything. But then the first few articles I wrote, things like I would write maybe a few sections in a chapter, and I send it to him. And I worked hard on them because first I want to impress Robert. It's like I don't want to think that I don't know how to write. He's a writer, so I'm working really hard. And that was before ChatGPT got. That's also such a nice thing, because otherwise I don't know if I was using ChatGPT, if I would have used it or not. But then he'd come back and say, "Oh, let's jump on a Zoom and talk about what you wrote." And so his reaction would be, "Well, I think it's interesting, but I really don't get your point. I don't understand what you're trying to say."
Oh, God.
In this. And I'm saying, wait, I spent a lot of time explaining what I wanted to say. Here is what I was trying to say. And I would explain it to him. Then he would say, "Oh, now I understand. So why didn't you write what you just told me?" And I say, I think I did. He says, "No, you didn't. You wrote something else." And this is for the first time, honestly, since high school, when I'm getting feedback on my writing. And I discovered that I have two modes, a mode of talking and a mode of writing, and they're not the same.
Mm-hmm.
They're not the same. I tend to be a lot more terse and brief in my writing, and I'm a lot more verbose and explain a lot more when I talk.
Mm-hmm.
And his advice to me was really simple. It's just write the way you talk. Just write it.
Okay.
And then you can fix it. That was a revelation, I have to say. It was really changed the way I was thinking about writing, because I was trying to structure these sentences and make it to be brief and so forth. And instead, it's just write it the way you talk first, and then you edit. And it was a really informative time that I spent with Robert learning how to write. And now I have this kind of like an emerging new passion for me to write more, because it's actually really fun when you do it that way.
And what's the trick behind? I'm asking for a friend. What's the trick? Did you record yourself as you were speaking and then maybe translating? Because
No, just not to spend too much time. Talk and write. Usually you don't have to, you could actually. That's a good way to do it, to transcribe it, to say it, and then it writes and so forth. But I would do is that just not really try to structure my sentences. I'll be thinking about how I'm saying it, and I'm just typing. And I type something really, really long, because and then I'll edit and fix, but the explanation is coming because I'm imagining that you're standing in front of me and I'm explaining something to you.
I can relate very much, actually. I'm very much an oral person. I guess maybe we're trained to that as engineers, to be very concise and get to use the minimum amount of words and even characters.
Exactly. And when you write equations, you try to be terse, and you don't want to. We are trained that way. And it's interesting to kind of write popular articles for other people. It takes different type of, and you have to have a lot of examples. People learn by examples, not just by conceptualizing what you do. So you have to throw in a lot of examples. It was interesting. It was an interesting learning experience. I didn't expect it to be. So kind of all in all, it almost doesn't matter like what the outcome. I really enjoyed writing the book in the process itself.
So in this other tangent, you touched on so many things that I actually wanted to ask you later. One being about the impact of AI systems roaming around our world, and also as a continuation of our conversation at ECC, but also the curse of big data, but also small data. What did you learn in writing? I would actually try to defer it to the end of this episode, not because it's less important, but just to also do justice to the body of work that you also contributed to doing since 2015, which is what we were discussing before. So as you mentioned, you became the director of IDSS, the Institute for Data Systems and Society at MIT. This was an institute that, as I understand, was across departments. It was a super entity, super in the sense of above, and it brought together many different people. Also, something that I would like to ask you later is implementation strategies, if you want to, actually how to form and train the next generation of researchers that will address those questions. But first, I would like to talk about, again, the paper that we mentioned before. So robust distributed routing in dynamical networks. I think we have to do justice to that. The second part of it got another Axel B. Award paper. And I found it particularly interesting, again, because we were talking about cascading phenomena and failures. That paper essentially makes some of these concepts very precise. I don't know how to actually start the conversation on this paper itself.
So I will tell you, I'll give a very quick overview of the work, and it's a body of work of several papers, right? But it's all kind of interconnected. The idea is that agents make decisions at the node when they arrive. Like, so we think, okay, pop it up a little bit, right? So we're talking about a transportation network. People are moving from, let's say, from one origin to a destination. And they have options of how to go. And so they have some prior information about the congestion of the network, maybe as a distribution, but also they learn information when they arrive to a particular node. Okay. And so they make a decision of which way they should go. The routing decision is a human decision. So it can be an element of many different possibilities. They could choose the path that they predict to be the shortest, or they can do something, a combination of that plus an exploration somewhere else. So they can be a lot of different types of strategy. And now we ask the question is that for a large class of human decisions, so human decisions are local, although they have a broad distribution of what goes on, they typically are local decisions. How robust is the network because of that? And what are the margin of stability, or basically how much disruption does it take to break the network? And so now what we have is two things that are interacting. One is a network structure, and primarily what we're going to see is some measure that has to do with min cut or max cut type thing, right? With the graph, basically saying what are the bottlenecks in the graph? The bottlenecks are going to always emerge to be the least robust part of the system. Imagine that you have a city that is developed on two sides of a river, and you have bridges. The bridges will become automatically bottlenecks, right?
Like Zurich,
like Boston and Cambridge, right? Boston and Cambridge are connected through 4 bridges, and from my office I can see the bridge, and I can tell you what's going on in the city. Because it's just at that time of the day, right? At a certain time of the day, the bridge is congested. I would say maybe there is a baseball game or there's a basketball game. You can infer a lot just by looking at that bottleneck. And Zurich is probably something similar. So what we try to do is put some rigor into the relationship between the class of decisions that individuals make at each point, okay, and the overall robustness of the network. And basically, are there new types of bottlenecks that can emerge, and how do we measure them so that we can characterize the robustness of the network? So that really is the work. And then later on, we did this by looking at cascades, so we understood information propagating backward because of congestions down the line, right? So now we allowed signals to be propagated backward and then affecting the decision strategy and seeing how that cascaded failures occur, which was the last paper that we wrote in this. So it was a sequence of papers looking at this, sort of adding, an abstracted mathematical structure on this particular problem and understanding this relation between the two. So that's really the composite work on this planning problem.
As you mentioned also, these kind of networks model different transport phenomena, not only traffic, but also data, production networks. These are some of the examples that you make in the paper. And also, I found interesting, maybe it's just because I'm not familiar with this area of research, but normally when we think about, for example, routing problems or network flows, one thinks about, as you mentioned, mean cut, max flow, or depending on what convention you take, but those are static problems, whereas you do think about dynamic problems, modeling the flow in the network with differential equations, essentially.
Right, exactly. Differential equations and the fact that the transients matter. So it's not like just a steady state static problem, right? And that's really kind of the model was trying to capture, because I think deep in my mind, when I think about a system, I don't think about just a bunch of constraints. I think about the time series and the transitions. So I think about the time aspect of it that matters, which I think you make a good point, because I think the max flow, min cut theorems and so forth are essentially about a static structure for these networks. And it's hard for us to talk about robustness
at the steady state.
At the steady state when the decisions are really made in real time. For us, it's really a real time issue. And if you have a breakdown in one of the links, well, it doesn't matter that happens in finite time. Who cares about what happens in steady state? The network is no longer the same. It's a different network. That link is gone. And that was captured in the cascaded failure. of how essentially we were showing how a failure of one link essentially resulted in a failure of another link, and then in a whole network collapse. So, a model that actually showed how this can happen and how you can actually minimize that by certain decisions made by. So now if you start informing the decision makers or giving them particular, so actually it's really interesting connection to a lot of the work that I did later on information design and data markets. So one of the things that kills us in a lot of these things is that all of the agents at the intersection see the same thing in terms of Google Maps.
Mm-hmm. Yeah.
Yeah. We're all using the same, either Apple or Google Maps. So we're seeing the same thing. So the signal that we are all getting is the same. And as a result, we all behave in a similar way. So we may all change to a different link, which then, of course, that link becomes congested. And of course, like Alex Baen and other people have shown how you can create new congestions that didn't exist because of these GPS systems, right?
That would have been one of my questions actually for you, and came up also, I think, in talking to Michael Jordan in the ECC episode. I mean, if we all receive the same algorithm telling us, the road ahead is congested and I don't know, the road to the right is better, we will all choose the right one, and then we will create a new congestion in that direction.
And I think that this is actually a really interesting problem that is emerging. And I know, for example, Ketan, one of the authors of this paper, has now a company that is thinking about this information design problem. So the information design problem is the following. What if actually every person got their own personalized information? Okay, and it's not impossible to do that. It's possible to do that. It's an automated solution, but it's personalized. And so you may get a recommendation to go to the right, and I may get a recommendation to go to the left. And of course, there's a very complicated thing. Why did you go to the right and I go to the left? We're all going to the same location. Maybe it sent you through a faster route and sent me through a slower route. Okay? And so we asked ourselves the question, first of all, in the well-being of everybody over many, many trips that we take, it may be that this is a better strategy than all of us going right and all left. In fact, you can prove that it is a better strategy. And I would not always be going left in the wrong direction. I sometimes may be going right. So you can say, well, okay, so maybe randomly shuffle people, and at some point, we'll all do well, better than if we waited in the congestion. But actually, there's also another layer to this that's really critical, which is something that happens in Boston. It used to happen. Now with global warming, it's not happening as much. We get the first snowstorm around now, maybe another 2 weeks from now. We'll get our first snowstorm. And we are never prepared for the first snowstorm. Never prepared. And so the weather is looking like it's going to snow. The city is functioning business as usual. We all head to work at 8 or 9 a.m. At 11 a.m., the mayor of the city shuts down the city and say, okay, this actually. And now everybody, there's this exodus from work back home. And it's basically usually the snow has just started, and so it's snowing on you and you're stuck in the roads. Amazing. I mean, it's crazy, right? Mm. Now the question is, well, could we have done it better? Mm-hmm. I would say, well, yeah. I mean, first of all, not everybody should leave at the same time. Maybe the people that need to go pick up their kids from school or something like that should leave first. Maybe people that are older, and there's a certain preference. The problem is that the system that we will design does not know the preference. It doesn't know the preference. So you have to communicate the preference. But if you communicate the preference, there's no reason why you're not strategic and you start saying, oh, I have to pick up my kids. And you have no kids and you go home, right? And so how do you incentivize truthful reporting?
Amazing.
And so that's actually the problem of information design, is that I want you to truthfully tell me what your preference is. And I'm going to give a recommendation, and over time, you are always going to benefit. That is, we call this constraint obedient. That is, you are better off following me than not following me, even though sometimes you're not going to fare out very well. And that's actually a new way of thinking about how to build these GPS systems to kind of mitigate the congestion and so forth, is this mechanism design that allows us to have this exchange of information. You give me information, I give you information, and everybody is happy. And there's no other way. You are not happier by giving me false information. And so that's the work that I've been doing in this data market and information design, is trying to kind of design these systems to be robust from that perspective.
It's wonderful because you're creating a perfect segue for me for the next publication that I had in line, which is precisely this one. So 2019, a marketplace for data, an algorithmic solution with Anil Agarwal, Thibaut Aurel, and Amir Nouripur, which I found very fascinating because you put your finger on so many critical aspects of modern society and how we as control theorists can have a say about those questions. For example, how to ensure that data is used efficiently and ethically at the level of, where we can actually say something, and that is mechanism design. So maybe I should let you illustrate what you did in this work.
Yeah, mechanism design is, we inherited that from economics, and there were two Nobel incidents. One was auctions, and the VCG, and then Mylson before that got the Nobel Prize on this. And it's a beautiful concept of saying, it's motivated by the second prize auction problem. And the second prize auction is an interesting idea, right? I can describe it very quickly. You're putting your house for sale and people are bidding on it. So before they bid, the idea is you can ask each person, this is a hypothetical thing that doesn't happen. I can ask each person that's coming to buy the house, how much is this house worth to you? And they tell me truthfully how much it's worth, and I sell it to the person that gives me the higher bid.
Sure.
That's not going to happen. If I ask people about how much is this worth, I don't know, give me half the price or something like that, right? So can I create a mechanism that elicits this information? Okay? So an auction seems to be a good mechanism, but always leaves you a little bit unhappy. If I say auction, so the bidders, you all bid for the house and the highest bid wins, you start thinking, okay, am I bidding too high? Am I putting too much money? What if I bid $1 million for this house and the next person put $800,000? I just put $200,000 away.
Yeah.
So you never really know what to bid. You always underbid because you're afraid that you're overbidding. Mm-hmm. The second price auction says the following. It says, okay, everybody bids. The higher bidder wins, but pays the second value.
Okay.
The bid of the second person, highest to them. So if I bid $1 million and the second person bid 800,000, I win and I pay 800,000.
Right.
Now I am comfortable bidding my value. Mm-hmm. I'll bid my value because if other people has higher valuation, then it's okay, I don't want it. And if people have lower valuations, well, I would never pay more than the next lower valuation.
Yes.
That's a mechanism. It elicits the valuation without ever asking for it.
Amazing.
You will bid your valuation without the person ever asking you about the valuation. That's a very, very smart way of deriving a mechanism. So it's strategy proof. It's the rational thing for you, and in a rational setting, obviously, it's the rational thing for you to do to bid your valuation. So that mechanisms can be generalized that way, where you think about, you don't offer a person a piece of information or a decision, you offer them a menu. And that menu is characterized by their personal information, by the preferences. So for every preference, there is a value. And now what happens, I design it in such a way that the best thing for you is to pick the one that is your preference. Same thing as I did with the second price auction. That's a mechanism design. Now, that's also a static problem. And what we have is a dynamic mechanisms. So we need to start thinking about how is that changing as a function of time, where also, what does that mean? It means I am a newcomer, and as I come every single time, do I gain the system over the time horizon, not just on the spatial horizon? Am I gaining over time? So we have to kind of do a lot of work for this, which is not yet done. Some of the work is done, but there's just a lot of work to be done to make mechanism design look like a control theory course, where you have a flow of information, mechanisms are being produced, and then strategy proof results are being shown. So the work we've shown is essentially in terms of how to sell data. So let me kind of tell you a little bit about that, because it's really interesting problem.
Yeah, that would have been one of my questions. So why data should be conceived as a commodity? And
Yeah.
I found particularly interesting in your paper the description of the specifics of data.
Yeah. So I think it's really interesting. Data in many ways does not have intrinsic value. If you look at a sequence of zeros and ones, what does that mean to you? Nothing. Absolutely nothing. And so data is only valuable in the way it's used. So you can say real estate is also valuable in the way it's used.
Sure.
You can say that, right? Except that the options are very small, either residential or commercial. Mm-hmm. And when a house is put in the market, it's either put as a residential or commercial. You don't have the option of two. Like we can, in Boston at least, you can't make it residential when it's commercial or vice versa. But in data, say you're taking my DNA or my genome description, my genome description could be extremely valuable because I have some rare disease.
And for an insurance company, for example.
For an insurance company, for a drug discovery, for drug repurposing, while your DNA may be useless because you're normal. You have nothing to show, right? Mm-hmm. Okay, it's the same data set by two different people has drastically different value because of its utility. Now, this DNA, mine and yours, is useless to a retailer. Totally useless to the retailer who's coming to buy data. Useless to a teacher who's trying to teach a class. So the context of utility of data is so broad, so big, that a market has to evaluate the utility of the data in order to price it. Without the utility, you cannot price it. And so that's why so when people in general, they're often very disappointed by buying data. Companies go and they say, okay, we need to understand customer data. Or they go to Bloomberg or to Reuters or something, and they buy stacks of data on people. And in general, they really can't do anything with it. Why? Well, it's stale, it's old, it's not relevant to our business, but companies convince them to go buy data. So there is a market out there for sure, but it's not created around the concept of how much utility you get out of that market. And how much utility you get out of the data depends on your preferences, on your usage, which is not known a priori to the market. So you come to the market, you want to buy data. I don't know what you're going to use it for. And I don't know how much you're going to take advantage of the data that I give you. And the price I should charge you depends on how much utility you get out of the data. And hence the concept of a data market, of a two-sided market where the market really is eliciting this preference. We're trying to understand how much value you can get out of the data. So it took us to mechanism design, which is the same question that I described before. Yeah, so that was the first paper. And then we kind of went into the role of competition and how competition increases the value of data. And there's a lot of work that is ongoing in that. And this has become, this is part of my work that is looking a lot more like a publication in economics than it would as a publication in fact, it is published in economic journals, right? It's not in control theory journals.
I was about to say that in preparing the episode, at least I would say the very recent phases of your career, you're almost turning into an economist.
Yeah, I mean, it's sort of interesting.
On the surface, at least.
Yeah, it's interesting. I hope not many economists are listening to this podcast, but I'm gonna put a plug to engineering. I love economics, but let me tell you, and not all engineers are equal, not all economists are equal. But when my kids were growing up, and I have 3 older kids, the youngest is 22, and the oldest is 30. Essentially, they're all studying economics. And I don't know if my wife agrees with me, but partially it's my influence in them. So I basically discovered economics in the last 15 years. And working with Asimoglu and some other economists like Bonatti and Roberto Redobo and a lot of economists that I work with at MIT. I learned from them economics. And I really loved it. And the reason I loved it is a secret I'm going to say on this podcast, which is I'm a terrible engineer.
That is questionable.
So I can't actually fix anything. I mean, as a real engineer, as a practical, I cannot fix anything. I can teach it. I can write papers, but I cannot fix anything, right? And so I was entertained by the fact that economists don't fix anything. They just explain it, right? And so I can explain what they explain. I mean, I can get into the same game, not like the best of them, but at least I can run with the crowd. And it's easy. I can explain when we have a financial disaster, I can explain cascaded failures and tell them this is what happened. I don't have to fix it. They don't have to fix it either, right? They don't fix it, right? Maybe regulations they fix. So I told my kids that this is a great field. You develop intuition, you learn a lot of mathematics, you learn statistics. It's a great field. But then I came back in full cycle now to say that but there's something about engineering education that is not there in economics or the social sciences that I wish that they would do more of engineering. We spent time in labs building. I built an amplifier and I built a lot of stuff and in digital, the analog days with op-amps and transistors. And then we built digital circuits and so forth. And we were going back and forth between what we build and the theory that we do. I had this wonderful example from one of my professors in circuit design. And because I was bad at building, I compensated by doing the analysis. So we had to build this 3-stage amplifier with feedback, which gave me a heartburn. I still remember it because this is like 40 years ago. It's not yesterday, But I still remember it because I can't get it to work. You're supposed to close the loop. But when I close the loop, I get oscillations because I have too much phase in my forward loop. And when I open the loop, I get good performance, but I don't get the sort of the decaying performance at the tail end. So I had to close the loop. So almost like I had to build 2 circuits. One is open and one is closed. But I couldn't close the same circuit. Anyway, I did my calculations. This is an anecdote. Ahead of time, I decided what the capacitors and the resistors I need. I did the analysis. And we're supposed to, right? It's not like and I did that carefully so that then I go to the instrument room and I'll pick devices and components that match my numbers and hopefully everything works. So my professor walks by and he's looking at my calculations and skimming through it and it's clean and I did that. And then he goes, what is this number that you have over here? 3.14 or something, He said, it's long. I said, that's pi. He goes, interesting. What's the error that we have in our measurements in the components? And I said, it's like 20 to 25% error. He goes, there. Next time, when you do the calculations, use 3 for pi. And he walked away. And then he looked back and he said, actually, use 2. And I think that this is also the beginning of my robustness training and this uncertainty quantification problems and how you go back and forth between theory and application, this exercise of going between the two. I always tell people that build important things and difficult things is that they're courageous. Real systems are scary, mathematics is easier, but that we are grounded in this interaction between the theory and the applied. I may not do applications like in the sense of building them, but you have a certain respect to the real system.
Indeed.
Yeah, and having dabbled with it. And that comes with the education. And of course, many of the good economists also have that kind of a respect, but engineers, all of them, you get trained the same way. And that's just part of our DNA. So I became full circle after my kids graduated. My youngest is still the last year. I told them, well, guess what? Maybe I'm changing my mind.
So we've been talking shy of 2 hours, so maybe it's actually a good time to start slowly to transition towards the end of the episode. One of the things that actually, in talking about these things, that came to my mind is that, in fact, it seems like you're also going back to the origin a little bit in some of your latest publications. For example, the paper Finite Time LTI System Identification, which is very much a core question of control theory. But also another publication that really piqued my interest was Causal Matrix Completion in 2003. I thought that was very original, at least the idea of building in causality in the matrix completion problem. For example, I think you had this example on Netflix sort of platforms and causality helping in predicting the missing entries. Again, there will be links in the description as always. But finally, I thought it would be nice finally to talk about, again, the book, Data Systems Society and the Data Nation podcast. We promised to talk about it. And in that book, you have so many different things that I thought would be worth discussing. One would be the impact of AI, for example, in our everydays. How do we build the next generation of, I was about to say engineers, but as you mentioned, they should be transdisciplinary. They should be trilingual. So how do we prepare the next generation to analyze and design these new sort of systems?
I think this is the challenge that IDSS has taken. And I wish that we were able to, but not yet, sort of take that to the undergraduate level. But right now it's still at the graduate level of thinking at how to build a trilingual student from a research perspective. This idea that there was room and has happened actually quite a bit of research where I call it multidisciplinary, where I team up with a doctor and we look at a problem. They know something, I know something, and we can do it. The problems of today have changed a lot, that you have to embody the knowledge of these different things. And so that's the transdiscipline, is that it's coming together. Data systems and society are coming together in a way that you have to think about the whole thing at once. The problem formulation and the right questions to ask is going to be really critical. And these are not just driven by minimize cost, maximize revenue or something like that. It's a lot more than that. It has human value, human mental health, human well-being, things that are destroying the next generation, but not our generation, long-term objectives. So the questions have to be raised with a good understanding. This is what I call ethical solutions. I don't call ethical solutions about avoiding the wrong. I think avoiding the wrong and doing good for society has always to be the thing that we do. Every technology we build, we can turn it into something horrible, but we're not supposed to. We should be doing things that are good for us. But there are things that are good for us today that are not very good for us in the future. And so that's the difficulty of this dialogue. So we try, at IDSS, the main thing is to say that can we develop a culture of people thinking that way? Because there are people who think that way. And there are researchers who do this. It's not like, it's just happened here. But building cultures, communities who have the same way of thinking, who feed into each other about this, is really the biggest contribution that this institute has provided. And I think I would urge that universities deviate a little bit from the models of the firm definitions of disciplines. Not that I think disciplines are not good. I mean, disciplines are very effective, and I write about that as well in the book. But this idea of bringing these different ways of thinking, let's not thinking about disciplines, but different ways of thinking together, I think is important. And this is work in progress. What we're doing at MIT is work in progress. And I hope that this would expand into other communities that would do something similar, and we stop burning. And there are expansions with other communities, but more of that almost in every institution, is to see this embodiment of society in the way we think about our problems. Every problem has to think about society, bring people into the mix right from the beginning. And what does that mean? Systematic way of thinking about human behavior, human reasoning, systematic way of thinking about incentive mechanisms, systematic way of thinking about behavioral economics. It's not just theory, it's a way of thinking about the problem. At the same time, when we are using well-formulated mathematics to solve mathematical problems that emerge from systems that have physics and good models and so forth. And I would say, my answer is that I don't have a crystal ball, but we're trying very hard. And what I am really encouraged by is some of the PhD theses that are coming out of IDSS right now that are just incredible in terms of tackling that middle, that space, that triangle, in a way that is rigorous and consistent and impactful. Not every PhD is in that triangle, but some of them are. And as you know, PhDs are a spectrum of either more applied, but this is, there's quite a few that are right in the middle, tackling complex issues of healthcare or democracy or institutional intervention with AI, a very interesting set of topics, right? And so I'm encouraged to see the fruits of some of what we're doing, but I would say it's still work in progress.
Fantastic. I mean, I agree pretty much with everything you mentioned. I have just 3 comments. One, essentially, it's just to connect also to a sentence that I found particularly beautiful in relation to ethics in your book, when you say, I'm not a sociologist or an ethicist, but it strikes me that technology moves much faster than our social and humanistic understanding of its impacts. And this is very much in line with what you were mentioning. In relation to how do we train the next generation, you talk about the importance of physical space for these interactions to happen. I think that's also, something valuable maybe for someone who will build, let's say, the new institutes of tomorrow that are in line also with this vision. And okay, this is more of a personal itch, the name actually of this transdisciplinary field. At some point in the book you write, one might aptly dub DSS as cybernetics 2.0, which I found amusing. Is that the definitive name?
Well, cybernetics, right? It was amazing what Wiener's talked about, sort of using systems to understand social behavior. And what was missing at that time was the data. A lot of that was based on hypotheses and so forth. And now we have the data. So cybernetics was, not many people like that name. So yeah, but cybernetics is actually an interesting, I don't know where it came from, but it's cybernetics 2.0 because now we are bringing people, systems, and data. And that's everything. What's left, right? But I think no field, no discipline or transdiscipline should be everything. Like system theory, one of the problems that we face as control theorists is that we are also generalists. So 3 years of your life, you could be working on chemical processes, and then you move and you start working on the grid, and then you move and start working on cars. You're a generalist. You have techniques that are transportable from one field to another field. So data system society is a general principle. But what I'm saying about this discipline is thinking about the underpinnings of how they interact. We need to provide people with ways to abstract this interaction, the same way we did in system theory, the same way information theorists did, right, in information theory. We need to do this in this hybrid field. And we don't know yet because it's a little bit more elusive when it comes to society. Not elusive in the sense that it's elusive because we don't know how to pin down society into a bunch of principles. And so that's where I think why I keep saying it's work in progress. I think that this requires a lot more thinking so that we can anticipate the impacts of technology on society, which we have done a terrible job so far. Since the Industrial Revolution, we have never predicted the impact of technology in our society. It's always after the fact, right? It happens and then we explain it and we try to mitigate and change it, right? And some of the changes like, when with automation that came in the early 1930s, 20s and 30s, what that did is actually increase the population in universities, right? Because people recognized that they cannot do the kind of manual work, then they had to go to the white-collar jobs. So there's an influx into universities. Now we're getting AI doing some of the white-collar jobs. They can write articles and they can write reports and they can do things. Okay, so now where do you go? Where do you go from an undergrad to a grad school? Or what's the effect? Okay, we predicted. There's going to be new jobs, but where are they going to be? Or are we all going to be people that are support people where this failed and I'm on the phone trying to help you? What's the new job? The future job, the future work created by AI, my opinion would be tremendous, but we have not predicted it because we don't have this understanding of the interaction between these components. And this is just as a social science question. A different question for us as engineers is architecting these systems and building them, guaranteeing their robustness. And the same stories occur, but now, bringing the people early on in the mix.
It's amazing. I fully resonate also with this deeper interaction or stronger interaction with the social sciences. I do think it's very important for training the future generation of engineers in this respect. I guess here we're really nearing the end of this episode. One question that I tend to ask to every guest, as you may be aware of, is advice to future generations, to future students. We did talk a lot about future generations. You've graduated over 40 PhD students, mentored over 20 postdocs, the majority of which is now in academia or in top tech. So I'm curious to hear what kind of advice would you have?
Well, if you really want my advice about what to learn, maybe read the book. I do say a lot about what students should focus on, what they should think about. I think there's a couple of things at the basic level. You do need transportable skills, but you need to understand, we talk about analytical skills. We want people to be logical and systematic in the way they think. Now, of course, mathematics helps you become more analytical, but there are other fields that can help you become more analytical. You need to educate yourself to be able to move with the times. Things are moving much faster than when I started. I feel, or maybe I'm just getting into too many things. I'm not sure. There's not enough time in the day to read all the things that are interesting that I want to read. But somehow having the ability to navigate complex articles and so forth without having to read them all in gory detail and understand what they're trying to do and recognize whether that's what you want to be exploring further or not is a skill that you acquire. And I would urge you to always think that way. But I do think that, again, advice is a dime a dozen and every advice is contextual and so forth. Maybe I will say what I tried with my own students, my own PhD students. And that is, I mentioned this at the beginning. It was very important for me that they do something on their own, that they do something that they're not passionate about, but that they invented, they thought about, they chose. Now, in the realm of things that I understand, that's not a lot, but they chose me. And so that's kind of tough. I mean, there's a huge number of things to work on. But at least in the realm of things I understand, I gave them full freedom to pick what they wanted to do. And I found that this is incredible. One, for them, when they pick a topic and they finally recognize that there is something they can do in there, it's a tremendous growth. Because you just imagine yourself, you come out of an undergraduate, you've been doing homework essentially, maybe you've gone into a couple of projects, and now I throw you in this field. It has papers, there are some companies there, and you have no idea. You have no idea what needs to be done. And I don't tell you what needs to be done. Maybe I don't even know personally what needs to be done. And then we begin a process of trying to understand where the research is needed and what are the loose ends or what are the new innovations that need to be done. And you recognize that and you formulate the area of research. There's just a jump in growth because then you can do this any other time in your life in a different context, in a different situation. You don't have to do this again. That you learned how to do. And then the process of solving the problem that you formulated and so forth, which typically is actually the easier part of it. And so with that process, though, comes a lot of frustration. Learning is frustrating. Learning is not all fun. And getting into the bottom of things and really understanding it well and understanding what's needed and it can be a lonely exercise and frustrating. Sometimes not too lonely, but sometimes lonely. So you go through this frustration, and I think, my advice to my students is not get too bogged down by the frustration. Everybody will get frustrated. And part of what we do is turning our frustration to something positive, something that we learn and something that we then become second nature to us. So not shying away from hard problems and complex issues, kind of staying with them. At some point, you may simplify them to come up with a solution. It's okay, because you do what you can, but don't shy away from the big problems and don't sort of try to do something where you never get to a closed door. You have to go to closed doors. And if it doesn't open, you have to change path and go to another door. And it's kind of a lesson in life, and it's a lesson in learning and so forth. And I've done that with my students. And I have to say that in that process, not only I've seen tremendous growth among my students, I've learned a huge amount myself. Every student has been a body of work that I probably didn't know from before, and just learned a lot from working with them. And which is great to know that this young person has been able to teach you so much. I mean, it's not something that happens all day. So that's kind of like maybe my advice or my recommendation, I would say.
So elicit internal motivation and don't give up when the PhD blues come, let's say.
Yeah, exactly. That's a good word, PhD blues.
Well, thank you so much, Munther. It's been fantastic to talk to you and also to have you here on the show. Thank you so much for joining us.
Thank you, Alberto. Thanks for hosting me, and good luck with future podcasts.
Thanks.
Thank you.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.